slide and probably camera view.
You can just are you able to?
Yeah, so I've shared my screen. In the chat, please let me know if there's double sound, and I'll mute. I might have two microphones because you'll see I've got a camera that's my phone, and then I've got my computer camera. But I'll be switching between those and turning that off as we go. I'm also going to record this locally, so if anyone is having connection issues, I'll make sure that there's a copy up on YouTube. Excellent. So welcome, everybody. My name is Jonathan Whitaker, as introduced. You can find me on Twitter, or Data Science Castnet is my blog and YouTube channel. Yeah, so I was a data scientist, well, I'm a data scientist and a consultant. I spent a couple of years working primarily on Zindi, which is why I was very much on Team Zindi when we were talking about platforms that try and feature kind of realistic problems in a more local context. I actually stopped work a couple of months ago to take a bit of a sabbatical to do some learning and kind of also just recover from some burnout. But yeah, so pursuing personal projects at the moment, and then slowly coming back into finding ways to do, yeah, more sort of education stuff, putting up courses, but also just, yeah, seeing what other different research directions I can take. Excellent. So we're going to follow on from, well, I guess I'll stay on the title slide for now. We're going to follow on a little bit, kind of talking a very high level tour guide sort of exploration of the kind of current state of the art in deep learning. My goal here is not to teach any of these concepts to a deep level, right? I don't want anyone to have their notepads out, like trying to write down equations or anything. This is the very high level overview. And then my hope is that we can keep this as discussion-based as possible. So maybe while I'm introducing and going through the intro, just to let me know that it's not only our panelists watching. If you're a participant, please put something in the chat, just so that I know that you can hear me, that you're able to put in questions. And then throughout the whole talk, I will try and pause as often as possible to give space for questions. Even if you have questions for our previous speaker that you couldn't get out in time, put them there. And we'll pause frequently. I do want to keep this like a back and forth. And because there's quite a lot of topics to kind of touch on, if there's something that you're specifically interested in, I think we're a small enough group that you can say, hey, actually, can you talk a little bit more about this topic here? I'd like to learn how to do that, or I'd like to know what your experience is, or that project you mentioned sounds really cool. Could you give us some more details? So I want to try and be very flexible in that regard. Yeah, so please, while I'm talking, 5 volunteers, give us some notes in the chat, just to know that there's that 2-channel communication. Excellent. Okay, so with that said, this is the plan. You can scan this QR code, or I'll put a link in the chat. So maybe let me make sure I can share. If you want to get these slides, they're not the fanciest slides ever, but the important thing is I've left sort of links and resources in there. So if you are interested in diving deeper in your own time, I've shared the link in the chat, or there's a QR code, just so that you can find things that I mentioned in passing. Okay, so it's going to be quite condensed. We're going to do the lightning overview, what is deep learning, although that's kind of been covered. Probably won't go much into the history because of the time. We'll talk about transfer learning and why that's such a key technology. Then we'll explore some of the more recent advances in language modeling and the kind of unexpected ways that those apply to various problems that we face. I'll give a brief look at some generative models, some of the latest, greatest, sort of more artistic and fun applications of machine learning. And then we can just chat and do questions and talk about where things are going or what would be interesting to learn. Okay, so with that, let's get straight in. So what is deep learning? You would have seen it kind of alongside or contrasted with maybe some of the classic machine learning in the other talks we had today. You might have seen diagrams like this. And a lot of people talk about how deep learning is inspired by the brain, and we have this idea of a perceptron with some inputs connected to other sort of neurons and information being fed through. And so it is. I mean, this little comic here is maybe my favorite depiction of this machine learning. You have your data coming in, and you do some matrix multiplication, and maybe you introduce some irregularities and non-linearities. But basically a bunch of linear algebra, and out the other side comes some answers. And when those answers are wrong, you backpropagate that error in fancy terms. You stir the pile until it starts looking right. Essentially, you find some way to update your weights or your values, whatever is going on in this big pile of algebra. And so those answers look less wrong. And by repeating this process, you end up with something that's able to take some data and make sense of it. And it's kind of ridiculous that that works. It seems like it shouldn't. It seems like magic, but it turns out that this is what is powering all of these advances. It's what's doing these incredible things so much better than any human ever could. And so it's kind of mind-blowing. And of course, it doesn't look just like this little diagram or like this pile, sort of complicated looking things. But in the end, it all comes down to that same idea, right? We have the deep comes from many layers. We have these layers and layers of operations that we do to incoming data. And at the end of it, it's been able to make sense of it in a way that the more standard algorithms like clustering or support vector machines or whatever, they just couldn't ever hope to achieve the kind of complexity that these deep models can. Yeah, so like I said, please put something in the chat. Any questions? I'm not seeing much activity. I think everyone's quite quiet, but please, we do want to have some back and forth. So any moment you see something that you didn't quite understand, or I say something confusing, hey, can you define what you meant when you said back propagating the errors, or where's the picture from? You know, just chime in anything that you want. Let's keep this discussion going. Okay, so now on to some history. And I'm going to skip over the early days. I took out some slides, but I do have a reference in here if you are wanting to read, going way back, you know, who first came up with the idea of a neural network, trying to represent what's going on in the brain artificially, you know, how did that evolve? But where I want to pick up is with this challenge of image recognition. And image recognition is not the only application of deep learning, but it's kind of the first one where deep learning suddenly leapt ahead of everything else that existed. So this person here, Dr. Fei-Fei Li, was one of the people involved in something called ImageNet, right? And this got put together and it got hosted as a competition. And the goal was to take an image and to assign it to a class, right? This is a picture of a car. This is a picture of a certain breed of dog. Maybe it's a sea snake or a chest, right? They had 1,000 different classes. And previously, this is around 2013, 2010, 2013, 2014. So before that time, if you wanted to classify an image, it's a very hard task, right? Because to us, two pictures of dog, we both say, well, that's a dog and that's a dog. But if you look on a per pixel basis, what is your reasoning for that, right? It's quite hard to turn that into a hard-coded rule. You can't say if this pixel is bright and that pixel is dark, then it's a dog because it might be facing a different way or whatever. So when I first got interested in image recognition, the kind of best thing that we had was creating these sort of meticulously tweaked features. We look for areas of dark and light that might be eyes and a nose. You know, they had something called Haar cascades, you know, and all these shift features and everything. Very, very complicated and tricky and very hand sort of engineered to try and make sense of images. And it didn't do very well. But then something magical happened in 2013, 2014, which is when a team managed to use deep learning, which had been around in theory for a while. But they managed to sort of approach it in such a way that they could train these models to do better than anything previously. So these handwritten sort of carefully tuned features were getting about 50% accuracy. They leapt to 65% accuracy. It was this massive increase in possibilities. And from there, you can see this is from papers with code, a bit of the history as we got better and better at doing this. We figured out more and more efficient ways to train. We figured out that more and more complicated architectures could sort of take advantages of subtle nuances in the data. Until today, these models do, you know, this is 90% accuracy across thousands of different classes of images. And if you've ever tried to do it yourself, I don't think you could match that model, right? This is not easy ones like dog, car, airplane. It's like 50 different breeds of dog, and sometimes very blurry pictures, and you're not sure whether it's a truck or a bus. So it's quite incredible how far things have come. And yeah, these have been, I mean, most of these models were convolutional neural networks, which were able to sort of identify patterns in different ways. But yeah, so this has been the last, what's that, 10 years, kind of the first time that deep learning has its niche all to itself, and it's able to do so much better than anything we had previously. And like I think Francis mentioned, this is a very different paradigm to traditional programming where it's a human being trying to come up with rules. Instead, this is us showing examples and having the computer learn a program that does what we want. So very, very exciting. And that kind of leaves us now today in the space of saying, well, what's actually possible? And the thing I want to do in this talk is go through what's happening, how we built on these ideas, what's happening in other realms, because this ImageNet moment is something you hear people talking about today with regards to text. And I think we are reaching a point where it's not only image classification that's going to be the key use case for deep learning. We're suddenly seeing speech, we're seeing text, we're seeing artistic expression, you know, self-driving, reinforcement learning, all these other areas are sort of reaching that same tipping point that image classification had back in 2014. So that's why I had a little bit of history here. If you want to read more, here's one of many articles. It's quite interesting to see how we had sort of phases of people being interested in neural networks and then kind of falling out of fashion and coming back again. Okay, a little bit of history. I'm going to pause very briefly in case anyone has any questions. We have someone using the Q&A just to let me know that they're paying attention. Thank you so much. I really appreciate it. I used to teach a lot last year when everything was online, and it can be quite intimidating when it's just a one-way blank street. So it's good to know that there are people following, and yeah, like I said, any questions that you have, any topics that you'd like, this is very sort of free form. Okay, perfect. Do keep those coming. Going to step into the next phase now, the next sort of transition, which I think is quite exciting. And it's especially important for those of us who don't have the scale of Stanford University and Google to be able to put together something like ImageNet. So we have the joys of transfer learning. And again, it already came up in Francis's talk. I think this is great. It's actually worked out well to have the two following after the other. So to achieve this high sort of fidelity image classification, ImageNet is something like 14 million images. And when they first trained the original neural networks on that, it took, you know, weeks of training to reach any sort of reasonable accuracy. And so the traditional wisdom was that we need a lot of data, right? An insanely huge amount of carefully labeled data to end up with a machine learning model, a deep learning model that could do anything useful. And the good news for us is that we don't always have to have that. So what we can do is take advantage of models that have already done some learning, right? We as humans understand this, that a baby has learned all sorts of concepts. When we want to teach it a new animal, we don't have to show it 10 million giraffes. We can show it a giraffe and say, this is a new animal called a giraffe. And because it's got previous experience learning what a cow looks like and a horse looks like and a dog looks like, it's able to quite quickly say, okay, this has 4 legs like a dog and a cow, but it has a long neck like a duck, right? And those two together, plus the fact that it's yellow and brown, mean it's a giraffe. So it's able to take these basic concepts that it's learned and apply them to something new. And it turns out we can kind of do this with these deep learning models. You take something that's trained on ImageNet, and this is a work from 2017 by this guy called Chris Olah and some sort of collaborators at Google Brain Research. They sort of dug into one of the early neural networks that was doing well at computer vision and said, what do these neurons actually mean, right? Like if we go back to a picture like this, although this is very simplified, what's happening at each of these layers? And in deep learning, even in those early models, we're not talking 5 layers, we're talking 10, 20, whatever, you know, very, very deep stacks of operations. So what's actually going on in those? And what they found was that the early layers were picking up features like edges and lines, right? And then as you get a bit deeper, it's identifying textures. Maybe it's grid patterns or something that looks like fabric or something like a smooth transition or a curve, right? So you have something in there that's maybe quite good at identifying circles. And then as you get deeper in the network, you know, starting to get patterns and textures, right? You can see some things that look kind of like a dog's nose or an eye or a button. And then as you get towards the end of the network, suddenly it starts being able to pick up on higher level concepts like eyes, like sort of breeds of dog, or this is people's legs if you look at it creatively. And this is just one way of visualizing what's happening. But the idea here is that by training to solve this one task, right, by training to be able to classify images in the ImageNet data set, this is not just learning some completely abstract representation of one class like dog. It's learning ideas like eyes and noses and shapes and colors and edges And it turns out all of those are useful for this task, right? It's very useful to be able to say, at the end of this network, if I want to say this is the dog, it's because I'm seeing high sort of predictions that it has a nose and some eyes and some fur texture and legs, right? So to be able to have those building blocks that it can use for that final prediction is very useful. And then if we take this model and we add on something to the end of it, we take away the dogs and cats and things, and we add on our new set of classes and some extra, sort of an extra section to the network, we don't have to learn all of these concepts again from scratch. We don't have to learn the concept of edges or textures or lines or circles or wheels again. So now when we're feeding it our different models of car, you know, we have Bugattis and Mercedes and so on. It's not starting from scratch and trying to learn what an edge looks like or what a wheel looks like. It can instead refine those concepts and quite quickly get good at this new task. So this is transfer learning. It's incredibly useful. And it means that we get these networks where we're able to teach it a new task, and that could be, you know, finding cancerous objects in a lung or spotting something happening in a forest from space, with relatively few examples, right? Instead of 14 million examples, you can do fairly well at the task with maybe 100 examples, or a few hundred examples or a few thousand examples. So quite incredible. I'm just going to check the question and answers because I saw something pop up there. Someone asking about a social media challenge, posting a photo from 10 years ago compared to the current. That might have been a very sneaky way to gather some training data, right? If you want to be able to predict what someone will look like in the future, that could very well be. I would guess if they were doing that, they were trying to, you know, when they tag people in images, be able to tag people in older images as well, you know, so it's not necessarily like trying to train a generative model, but definitely trying to say, if we want to tag your friend Sophie, you know, that needs to be when she was younger and older. Yeah, so that's almost certainly data gathering. Are we to worry that one day we'll wake up and find that machine learning systems have learned bad patterns and are performing contrary to what we expect? Are there any constraints to prevent this? So this is a big deal. There's already issues coming from this. And it is something that I think people need to be aware of. And that's why, you know, you see everyone who talks about learning data science and so on, they try and include this idea of ethics and, you know, sort of addressing, ethical concerns and sort of constraints. Because, for example, some of the models we'll look at, if you're training a model to say, this is what a human looks like, right? And you can imagine down the line, this could use transfer learning to do pedestrian detection in a self-driving car. So this is what a human looks like. And your data is based on pictures on the internet, right? What happens is that, well, maybe in the States, they've had good internet for many years. A lot of people upload a lot of pictures of themselves. And so there's a lot of pictures of white Americans. And in Africa, broadband has been around a lot less, you know, things are a lot slower. There might not be that many pictures of people with darker skin, right? So if you train a model to identify what a person is, but 90–95% of your people are white or light-skinned or some specific ethnicity, that model might get really good at detecting white people and not so good at detecting other people. And now you put this in a self-driving car, and you're in an issue where potentially you have a bias. It might be good at avoiding pedestrians in general, but worse when they're of a certain color, or worse when they're older, because maybe older people don't post on Facebook as much. You know, you can get these kind of inbuilt biases. And I think if someone is thinking about that, they're just going to say, hey, this thing is like 99% accurate at detecting people. Let's deploy it. You know, you really have to be careful with something like that to say, is this going to affect people negatively? Is the way this data was gathered going to mean that it has a bias towards certain groups? Is that going to mean that there's a shift in dynamics of power, or of someone being harmed, or of unequal harm coming to different groups? So it's a very nuanced issue, and I think it's one that people are already facing. Then we have a question for the previous speaker. It mentioned that AI can be used for healthcare and medical imaging. What is the approach being considered to minimize costs while using less costly devices? So maybe Francis, do you want to step in and answer that directly, or do you want to just answer it in chat?
Sorry, come again.
So the question is around smartwatches detecting, you know, these medical issues. And so it says, considering that AI is aimed at reshaping the modern world at a lower cost, Those devices are quite expensive. So what is the approach being considered to minimize costs while using less costly devices?
That one is it's tough to say, because when you look at our specific, like for example, it's not each and every smartwatch, for example, that has such AI capability, and it's not each smartwatch from Apple. I was just specific about Series 5. So I'm not really sure about what is being done to make it maybe some more, maybe less expensive so that people could afford it. Perhaps other companies, for example, Fitbit, if you look at their fitness band, it is actually way cheaper than Apple Series 5. So I think it will have to depend on the branding. I'm not really sure what is being done, but for us, I know there are certain brands that have cheaper products than other brands, but the capability also matters. Like if you look at what Fitbit is able to do compared to Series 5, specifically for detecting heart-related conditions, you find that the price is worth it. And just last year, it was able to save someone from stroke. So about to make it less costly, I'm not really sure what is being done. But what I'm confident is that there's already research going on. I don't think it's only Apple that is developing such products. There's already research, and also from the academia side, there are a lot of groups that are working on healthcare, vital signs monitoring, and IoT and the likes.
Cool, thanks, Francis. Yeah, and as you mentioned, like a watch is already a lot cheaper than a full-time carer or something like that. So I think we'll just continue to see that trend down. Lovely. Okay, I'm going to try and speed up just a little bit, but to finish this section on transfer learning. So here's a more recent sort of example of a fancier network that's able to learn even higher level concepts. And they found that there's neurons within there that react to something very sort of like a real broad concept. So not just something like an edge or a corner, but either a picture of a banana or a drawing of a banana or a picture of the written word banana. So it's able to associate all of these disparate concepts together and learn these very interesting representations of an image. And so I mentioned that this is interesting because we can reuse these networks for tasks where we might not have a lot of data. So examples of this we've seen through Zindi. We were doing things like, identifying potholes, right? You take a model trained on ImageNet, you retrain it with a few hundred pictures of potholes and no potholes, able to quite quickly learn. Same with pulling different animals apart, license plate recognition, mask or no mask. And it doesn't always have to be classification either. You can use these same representations for things like image segmentation. So this is a model able to pick out which parts of an image are vehicles or trees or people on the road versus off the road, buildings and so on. We've also seen sort of applying the same concept to different types of disease on crops, and even going a little bit further, kind of abusing it, turning things that are not images into images. Right? These are bird calls represented as spectrograms. But again, if I feed this through a network that's been pre-trained, it does still have detectors that could maybe detect sharp turns, blocks, fuzziness, different textual elements. So it turns out that that's able to do fairly well with fairly limited training examples. Now, of course, there's better models for audio than just using an ImageNet model, but it does work. And that's, again, the title of my talk, the unreasonable effectiveness. It seems crazy to me that it does work so well, but that's the benefit of having pre-trained these models on such diverse data. We can then apply them to new tasks and get pretty good performance. A final couple of case studies, which if you're interested, chuck a question to me on the chat. We did a collaboration with Sansa, where the model was able to learn to identify informal settlements. And we found that actually their labels for where the informal settlements were a little bit out of date. There were some they'd missed. Or the classic that everyone did during COVID, can we identify COVID in X-rays? There's all sorts of caveats around the kind of health data and what conclusions you can draw from your model having a certain accuracy, but it's kind of a fun task anyway. And it's an interesting one to me because, you know, I can kind of classify dogs versus cats. I could learn quite quickly what wheat rust looks like in a picture of wheat. But looking at these x-rays as a non-health practitioner, I had no clue, right? And so this model was able to get 80 or 90% accurate really quickly, and I was not. So it's an example of the computer learning really well. So lots and lots of applications of transfer learning. If you're interested, I'm going to shill for this particular course. I think they're one of the best ways of taking you really quickly through everything you need to put transfer learning at the sort of state-of-the-art, as good as you're going to get level into practice really quickly. I really enjoy the way it's structured, highly recommend. And they have a series of videos. Then someone says, is there a platform where I can find free data? My next slide is datasets. Yes, so there's lots of datasets for computer vision. You could look at sort of classics, like I mentioned, ImageNet and so on, but then there's also lots of other examples that you can use to actually put it into practice. If you're taking the Fast AI course, you'll see, you know, classifying dog breeds or whatever. But you can also try out, there's lots of competitions. So on Zindi, there's a whole list of, if you click on this link here, the computer vision challenges. So those are examples of data sets, like there's one with people wearing masks and people without masks, and you know, you train a model to tell the difference. But yeah, there's a whole host of data sets out there, especially for something like image recognition. There's lots. You can find one specific to cars, one specific to, you know, dash cams where you're trying to classify different things, one specific to space. So in the dataset section here, I think I mentioned SpaceNet have lots of like remote sensing imagery that's been labeled with different land use types or something like that. Very, very useful stuff. But yeah, there's some places to go try it out and explore. The Spot the Mask one, I did some getting started tutorials on there. But there's plenty of places. If you take the course, you'll see examples. If you go online for image recognition, you'll find millions and millions of examples there. Cool, so that's transfer learning on images and the ways that you can apply it. And it's really fun that it's so broad, right? You can turn a bird song into an image and classify that. And you can, I've seen people use mouse movements to draw a picture and classify that. It's very, very broad and turns out to be quite a useful technique. Any questions, any further questions on that? Right, I'm keeping an eye on the question and answer in the chat. So if you do have ones, even if it's on a previous section, I'm happy to like recap and review. But I'd now like to move into a different domain. And we'll kind of, again, keep going fairly fast. But if there's something that's interesting to you, like latch onto it and tell me, and we can spend more time on that and less time on something else. So we're now going to talk about language understanding, language models, and how they sort of spun out of some of the same ideas that we've been talking about. And how, again, we can kind of apply these to novel sort of problems. So the kind of question that sparked these, I guess, was people saying, can we do transfer learning for natural language processing? And it had been proposed, I think, as far back as like 10 years ago, but it was much more recently that it was shown that actually this can be done and it can be very effective. So you had ULM fit paving the way, and then all of these transformer-based models, BERT, Roberta, Albert, GPT, GPT-2, GPT-3, all of the hype. And so they all build on the same kind of key idea, which is to say, instead of taking, like with the images, right? We had images with a label that someone had to manually go and put. With language, it can be quite hard to find labeled data, and it's quite hard to then transfer it to different tasks. But they said, well, what if we just take raw text, right? We just scrape the whole internet or all of Wikipedia or whatever, some giant corpus of text, and we feed the model part of a sentence, and we ask it to finish it or to predict the next token. So if I give you, as a human being who understands language, this sentence, it looks like it might rain. You'd better take an. Anyone want to guess the next word in the chat? I'll give a very short time, so type really quickly. Umbrella. Hey, that was quick. Excellent. Yeah, so we have a guess, right? Probably umbrella. It could be something else with a lower probability. It might be, yeah, a raincoat or an Uber instead of walking. But the point is that we can do this because we understand the sentence. And to be able to do this task well, we've got to be able to look not just at the word just before, right? An is useful if we said it might not be perfect English to say umbrella, but we also want to be able to understand what is rain and what things are related to rain. And you better take means maybe it's an object. So to be able to do this task well, you actually have to understand language quite well. And the training data is effectively free because you can just find some text and cut it wherever you like, and then ask the model to predict the next thing. So this basic idea gives us models that are then able to, with surprisingly high accuracy, predict the next word in a sentence or the next token in a sequence, if you like. And what's cool is that by doing this, they learn a really, really great underlying sort of representation of the language. They learn ways of taking a set of words or a sequence of inputs and representing that in something that encapsulates its meaning, right? And then you can take that model, just like you can take one that's trained on ImageNet, and you can repurpose it for a different task. And these turn out to be much better than anything we had previously for translation, for autocomplete, for error detection, for text generation, for question answering, because you can say, if I give it a piece of text, the President of the United States in 1953 was, if it's learned well enough, it would then give you the answer, whoever the president was then. Now, it might just say some random president, right? There's no guarantee of truth. But that's an example of it's been able to learn these concepts so well, what's related to each other, presidents in 1953 and all of that. It's going to say the president was so-and-so. So very, very powerful concept. And you can reapply these models then. They're available just like the trained image recognition models are available for your own use and for repurposing. You can retrain a model to take in a tweet, right? It's going to represent that tweet in its internal representation. And then it's quite quickly able to sort of relearn the new task of, is this pro or anti-vaccination? Or is this a positive review of a movie or a negative review of a movie? Or is this someone who should be banned from our platform? Or a tweet that we should promote on our homepage, right? So you can have all of these different tasks done, and that includes translation. The other excellent thing with this pre-training technique is that whereas previous things require lots of labeled data, so for example, for translation, you want books that have been translated into the target language, right? So that you can train the model, here's two sentences, one in English, one in Tonga, this is how they go together. With this language modeling approach, all you need is just the plain text. So you can take everything that's been written in a given language and have it learn a representation of that language in such a way that that representation lines up with the representation of a different language. So by doing this pre-training, you're able to end up with translation models. They still need some direct labeled data, but they can do it a lot better than previously. And this is what's being used to push the state of the art, especially for under-resourced languages. It's a very, very exciting field. And yeah, there's examples. This was one. We've done a couple of like classification challenges. I think Zindi's great about like trying to find non-English data sets. But the crazy thing with this approach is that it doesn't just work on human language, especially doesn't just work on English, it works on other languages. But it also works on, like, this is an amino acid sequence for a protein. And you can train a model to predict the next amino acid in a protein sequence. Then you can take that model and retrain it to predict the protein activity type, right? So you can check out my blog on this subject. We did a competition, I think, as part of a hackathon. But yeah, it turns out these kinds of language models, these same approaches, do really well at these very diverse tasks, right? Oh yeah, this was it, the kinase classification. But you can do exactly the same thing, but with representations of music. And I'll show a little bit later, training a model to generate music. So it's the same idea, right? You have a sequence of inputs and then you're trying to predict the next token. But it turns out to be a very powerful way of training models without having to have tons of labeled data. And then going back to the idea of transfer learning, you can reapply that trained model with its sort of internal representation of the world to a new task. And by the way, this also works for images. So you can cut out bits of images, have the model complete. And to do that completion, you have to understand what a golf ball is or what a church might look like. And so that's sort of a big advance as we see people getting good image classification scores without 14 million training examples, right? They just have it look at lots of images that have been deformed and trying to fix them. So really, really cool field. If you're interested in language models specifically, Hugging Face is kind of like the company doing a lot of work making those more accessible. But there's also a couple of others. I know Simple Transformers kind of packages Hugging Face. FastAI have an excellent natural language processing course as well. And they have lots of language modeling features. They also kind of like kicked off the idea. I don't think they get quite enough credit for that. Yeah, so check out the NLP challenges on Zindi for some practice. I've linked to some kind of common data sets, but as mentioned, the kind of fun part is applying these ideas to local data sets. So you can find lots of tutorials sort of classifying the sentiment of movie reviews, but maybe you could build a local data set in your own language of, you know, comments on a Facebook page, right, in a Zambian language that are positive or negative, and apply those same techniques there. And you could use a pre-trained model in that language, or you could find one that's close, or you could just try retraining a model. It's kind of amazing. Even across languages, having this pre-training, it really learns patterns of speech and language that can be useful even in a totally different language or context. Yeah, so that's trying it out. That's kind of language modeling and this ridiculous idea of just training effectively a fancy autocomplete, giving us models that are able to do all of these other tasks. Okay, so anything other than autocompletes of my umbrella sentence? Loving the interaction. Yes, I agree with you, Joseph. Great to have people commenting. I'm going to dismiss these dismiss these umbrella ones, but if anyone has any other questions, feel free to throw them up there. Better take the bus, better take the train. Okay, I'll keep an eye on that. Again, if you have questions about language modeling, or you wanting to find more about maybe data sets locally, pop the questions in the chat. The final section, how am I doing on time, Joseph? Have I got, I think we're aiming to finish it by about 4 to go into the lightning talks.
Yes, so time-wise, I think you're good. So maybe we can have at least 4 to 8 more minutes, and then we can move on to the lightning talk. Okay,
cool. So I'll skim through. All right, now has anyone noticed that my backgrounds in my titles aren't quite static? So I had fun. This is like, I spent more time on this part of the slides than the rest of the slides, if I'm honest. But this is the output of a generative model. You can play with it online at artbreeder.com. Really fun sort of artistic exploration of what we can do in terms of generating synthetic images and then manipulating those images. So I'll talk about that, but first to go back and link with our previous sort of 2 discussions. So one of the things with a language model that's trained to predict the next token in the sequence is that it makes a really good way of generating content, right? If you give it the start of a story and then have it predict the most probable next token again and again and again, you end up with something that's quite often surprisingly cohesive. And so AI Dungeon is a sort of game built off of that. You just talk in natural language to this model, and it sort of tells the story with you of what's happening in this game. So you can say, I pick up my sword and run outside, and it'll continue that story. Outside is a troll. The troll attacks you. You can say, I set my sword on fire and slice the troll's head off, and it's going to carry on the story with you. There's been some controversy because it turns out it's very good at completing whatever story the user puts in, and some people have pretty dirty minds. But they've kind of sanitized it a little bit, and it's a really fun exploration of where these models go. So that's using these models that just predict the next token in the sequence. My example of that is training a model on Irish music. We don't need to watch this now, but if you want to go listen to the background on that, basically just feeding in a whole bunch of tunes, having it predict the next note in the sequence, same sort of idea. So that's kind of an obvious application, right? That's something we get by default with these models, is that they're able to generate plausible sounding continuations. But we start to see a lot more crazy stuff happening in terms of what people are doing with both image and text models to generate new and interesting output. So this is an example, a guy called Jason Antic running de-oldify. They've now partnered with a firm called MyHeritage, and they've trained a model to take black and white photos, old photos, and put them back into color and make them fancier and higher resolution. And you can do this as a supervised learning problem, right? You can take an image, turn it black and white, and then say, here's a black and white image, here's the correct image as the label, learn how to translate between them. But it turns out this has sort of limits. And so the technique that him and lots of others use is to have multiple models sort of working in tandem. We call this a generative adversarial network, right? Where you have like a critic that learns to tell what a real picture looks like versus a fake picture, and then the network that tries to fool that critic. And so they learn together and they get better and better. Very, very cool technique. I'm not going to go into the details now, but this allows kind of image transformations like this to happen. It also allows sort of more creative ones. So you have a network that can recognize the content in an image, right? Me giving a thumbs up. Another network that's more tuned to artistic style. And by playing them off against each other and using some techniques to sort of generate an image out of this, we can get some really cool artistic output that doesn't look like, you know, maybe it looks like in the style of a famous painter or whatever. Very, very fun, very creative. Again, there's a website if you want to go play with it. I'll also link later to a notebook if you want to see the kind of code that could generate this. And these generative networks have been pushed really far. This is not a real person, right? This is from thispersondoesnotexist.com. So this is an image that's been produced completely synthetically by a generative network, and yet it looks like a real human being. And you see these being used by sort of social media bots and stuff. But it's also really useful to be able to have a picture that you're not going to offend anyone because this human literally does not exist. Then more recently, we've seen some great advances taking these generative models and finding ways to kind of steer the outputs. So you have a model generating an image, and it's generating that from a position in what's called the latent space. And people have found ways of shifting that so that you get an output that looks older or younger, or more masculine or more feminine, or longer haired or shorter haired. If you look back at the images of this, I was just shifting it so that you have more or less vegetation, right? Let's have less vegetation, more architecture, less trees, more green, and so on. And so this is coming into mainstream products. If you're a Photoshop user or Luminar AI, you see these amazing sliders. You know, maybe you make someone smile or change their eyes, make them wider or lighter or darker, change the background. So kind of incredible finesse and control we're getting over these generative models. And then, you know, obviously it's the internet, so people find all sorts of silly uses for this. We have a model that's able to sort of find representations of two different faces, remap them onto each other, and of course you end up with people with cats on their faces, or videos of people that look like Tom Cruise who don't look like Tom Cruise in real life. So very, very interesting space. A lot of potential good uses, a lot of potential bad uses. Everyone's, I think, familiar with the potential abuses of something like this, because you no longer have control over where your face appears necessarily. But I'd like to focus on the positives, and then just as a sort of final view in this section, what's like next in line in terms of generative models is being able to go not just from an image to a slightly different image, or generate an image that looks plausible, but now combining the language modeling and language representation learning side and the image representation and understanding side, smashing those together and learning to find representations of text and representations of images that map the same concepts into the same place. And then using that for generation. So this is some kind of incredible work by OpenAI. There's some other labs doing similar stuff. But I would just suggest, you know, in the interest of time, go check out both DALL-E and Clip, the sort of two models they talk about, and just marvel at the examples, because these images here were generated from this text prompt. So an illustration of a baby daikon radish in a tutu walking a dog, right? This is not something that a human drew. This is not a picture that it retrieved from the internet somewhere. This is completely novel content generated from this text. This text was the input, this was the output. An armchair in the shape of an avocado. These are not real chairs, products that people have made. These are completely synthetic images spit out by this model. The storefront that has the word OpenAI written on it, right? These, you can imagine the utility of this for someone like a product designer who quickly needs to mock up, you know, a street scene or an interior, right? You could enter literally just enter text, get back images. Here it's given half an image and it's asked to kind of complete it based on some text, and it's able to complete it in different styles. Just kind of mind-blowing, right? And the way this works, and I think I link to this as well, a slightly different, newer version of this, just learning to associate the text below an image and the actual image, and to learn a representation of both that gives you all of this creative possibilities. So very, very, very sort of incredible use case. And I think kind of mind-blowing from a creative point of view, and from a sort of content or, what is it? What does it mean to have an image? It's like we can now just generate these things because we've got so much training examples, and these models are so good at learning nuanced concepts that we get something that we can kind of steer creatively, and it's really, really cool. Some of this is still behind, sort of, it's not released yet. I know DALL-E, you can't really play with it, but they have released the weights to clip, which is this sort of model that says how closely an image and a text pair go together. So you can use this, right? You can start with an image of noise and a piece of text. I gave it a friendly spider sitting on a flower. And over time, you can see the two sort of converge, and you end up with a picture that kind of represents your concept. And people are having a lot of fun with this, right? I mean, this is kind of meta, using a language model to generate some sort of pseudo-religious text, and then feeding that text into an image generating model and using it to generate these kind of trippy pictures. So people are having all sorts of fun, but I think it's kind of an early glimpse as to what could be, and what could end up being a large part of the kind of creative space, using these models that have such interesting understandings and representations of the world and such cool generative capabilities, and then just artistically steering those as a human being, rather than having to like manually create every image that you want to use. So very fun space. And this is kind of like, to me, I mean, it's much less easy to see useful applications of this for like our local context compared to, say, image classification, right? We can do full armyworm detection from images. That's very obvious concrete benefit. But I think this kind of fun stuff is also, it's also driving interesting research, and it's also feeding back into previous, more sort of directly applicable fields. And it's really fun to play with. And it's a good way to get people inspired and interested in AI. So here's some links if you want to go and play with various examples of this. If you look for StyleGAN interpolation online, you'll find tutorials and all sorts of frameworks. It's a very fun kind of space to mess around with, and it's kind of a nice way to get a bit messy and down and dirty with more complicated architectures and things, without necessarily trying to solve any real world problems. So if you need something inconsequential to work on, highly recommend. All right, questions on that final section, generative stuff. Thanks. It's interesting. Love it. Good to know there's still people online. You guys are good at interaction. This is great. Does anyone have any sort of further thoughts? I guess I could talk more about the previous case studies with Cindy that we did, or past projects of mine. But otherwise, yeah, whatever, any topic is open. And I think we've still got maybe a minute or two before we're going to move on to the lightning talks. So yeah, got time for a couple of questions. Are all these links available on the slide link you shared with us? Yes, wherever possible, anything in red is a link. And I've tried to put sort of direct attribution. I might have missed one or two things, but I think I got most of them. So the slide link I put in the chat. Yeah, you should be able to go from there. Is there anything like trial for the resources? I'm not sure which resources you mean. Some of these, yeah, like I said, you can go and see their examples, but you can't generate your own. But there are others where you can just play around and explore. So, and I think as we go forward, quite a few of these are fairly new. Give it another year, and these will be built into, you know, an online photo editing tool. Okay, for deep learning, is the focus mainly on detecting different imagery, or what? So image recognition, like I said, was kind of the first big application. So going from an image to some output, whether that's estimating someone's age, or predicting what the yield of a field of crops is going to be, or saying what type of dog this is. But deep learning can be applied to lots of other things. So you can use it to, for example, identify words in speech. Facebook has just done some amazing work learning how to decode different languages and kind of like add the auto captioning to a video and stuff like that. But you can also apply deep learning back to sort of more standard machine learning stuff. So you can use it for classification of business transactions, if you like. You can use it for time series classification is a big field. You've got, you know, vibration sensing from a turbine and trying to identify whether there's abnormal, you know, vibrations or whether it's just normal operation. So all of those other tasks deep learning also applies. A big area that I haven't talked about is reinforcement learning. So learning to operate within an environment by trial and error, and then, you know, every time something goes wrong, updating and improving your model, and then doing better next time. So we see, you know, deep learning models playing games and steering cars and driving industrial processes and getting higher and higher efficiency. Yeah, so it's quite a broad area. And it turns out, again, this whole talk, it's kind of, it's annoying to me how well this works across all of these different disciplines. Take some data, feed it through a bunch of linear algebra, see how close the answer is to the right answer. If you don't like it, adjust everything in a sort of controlled way. Try it again. If you don't like it, adjust it some more. Repeat a few times, and you end up with something that's able to solve a whole lot of different problems. Cool. If there's further questions, do chuck them in the chat there. I also wanted to say, you know, like, so I've tried to put some hints as to where you can test things out. But I'll also, I mean, I shared my Twitter handle there, or if you guys want to get hold of me, I'm sure the organizers will have my contact details. You know, so if you've got a more specific domain or problem that you're trying to look at, I'm also happy to chat sort of more specifics of like libraries or, you know, approaches that you might take. This has been very high level, I know. So if you're kind of interested in digging into the nitty-gritty, I think you're welcome to reach out and chat outside this forum.